Today we have Florian Richter from Northwestern University, who is telling us dynamical generalizations of the prime number theorem and disjointness of additive and multiplicative actions.
Thank you very much. Thank you for having me. Today I'll be talking about joint work with my PhD advisor, Vitali Birgelsen. And I understand this is a number theory seminar, but there will be a lot of dynamics. So if there are any questions whatsoever at any point, please just stop me and ask. So I want to start with a little bit of background and history in number theory. And to begin with, I want to remind everybody what's the omega function. That's a classical object of study in multiplicative number theory. And so capital omega of n is just defined as the number of prime factors of an integer n, and in this case, counted with multiplicities. For instance, omega of 1 is 0 because there are no prime numbers dividing it. Omega of a prime is 1. Omega of the product of two primes, or prime squared, is equal to 2. And more generally, if you understand the prime factorization of an integer, it's very easy to calculate the value of omega. We just sum up all the multiplicities of all the prime factors. And so it's a central question in number theory: what is the distribution of the number of prime factors? So yeah, what is the distribution of the values of omega of n? And to give everybody a little bit of an idea of what this function looks like, I included here a graph of the first 200 integers of omega of n. I understand this is not very representative because, for instance, there is a disproportionate amount of primes within the first 200 integers. Nonetheless, you can already see a little bit what's going on here. Overall, omega of n is growing. In fact, it's growing like log of n. But besides the average growth, it behaves very randomly. And that's in line with the general heuristic that people have about the distribution of omega of n. So it's understood that the values distribute randomly. They don't follow any kind of pattern. I've also tried to express this a little bit more dynamically, especially with people who have entropy in mind. Another way of thinking about that is, suppose you understand the values of omega of n in the past. So suppose you understand omega of n minus 1, n minus 2, and so on. Can you somehow predict omega of n? And the overall understanding is, no, you cannot. So it behaves random in this aspect as well. Okay, and why is this interesting? Why are people interested in the distribution of omega of n? Well, it turns out it's closely related to the distribution of prime numbers. And so here are some classical results from multiplicative number theory. So like I said, this is related to fundamental questions about the prime numbers. And to state the first result, I would like to remind everybody what's the definition of the natural density in the integers. I just denote it by d of a, and it's defined as the limit of the proportion that a occupies in the first n integers. In general, this limit might not exist, but for all the sets I'm considering my talk today, this limit will exist. So I'll just always write d of a. There should be no ambiguity. Okay, and so it was observed by von Mangold and Landau more than 100 years ago that the following statement is elementarily equivalent to the prime number theorem. Namely, that asymptotically, there are just as many integers with an even number as prime factor as there are integers with an odd number of prime factors. That turns out to be an equivalent formulation of the prime number theorem. Okay, having this formulation of the prime number theorem in mind, it's natural to ask, well, since omega of n equally distributes in evens and odds, maybe it does the same thing in other residue classes. That's another classical result attributed to Pillai and Selberg. And it says exactly that the values, the numbers n, which omega of n is congruent R mod m, has the density that you expect. It's 1 over m. So that can be considered a generalization of the prime number theorem. And there's another well-known result that I want to point out. it uses the notion of a uniformly distributed sequence. So let me remind you what that is. A sequence of real numbers is said to be uniformly distributed if it satisfies this property here. But what this essentially means is that x of n equally disperses throughout the 0-1 interval. And here's the result due to R dash n to lunch. And it says that if I have an irrational alpha, and I look at the sequence omega of n of alpha, so that's another way of studying the distribution of the values of omega of n, it's uniformly distributed mod 1. So there's no bias here. Every interval gets the same chunk of numbers there. Okay, and so what I would like to do today is I want to take those classical results from number theory and I want to look at them through the eyes of ergodic theory. And to start off, I want to introduce the setting that I'm working with. Well, let X be a compact metric space and let T be a continuous map on this space. To me, that's a dynamical system. It's nothing more, just a compact space and a continuous function. That's almost all you need to know. Something I do want to emphasize is that I want to think of such a dynamical system as an additive topological dynamic system. In particular, any map like that induces an action of n plus. And I will refer to this as an additive topological dynamical system to avoid confusions later on, because later on in my talk, I also want to talk about other actions, multiplicative actions to be precise. Okay, so this is a dynamical system. And by the Bugolov-Krylov theorem, any dynamical system possesses at least one invariant measure. So a measure on a Borel probability measure on a dynamical space is called invariant if its push forward under the transformation remains the same. So T applied to the measure is again the measure. That's what it means to be invariant. And there are certain class of systems called uniquely ergodic, and those are the ones that have exactly one. So we know every system has at least one. There are some that have exactly one. Those are called uniquely ergodic systems. And our first main result, that's all you need to know for the statement of our first result. It's about such uniquely ergodic systems. And it's somewhat of an ergodic theorem for such system. It says that if I looked at this Birkhoff ergodic averages, but instead of along n, I look at long omega of n. So those are forward iterates under the transformation along omega of n, then this converges to the right limit, which is the integral of f. You should think of this as an ergodic theorem. Why is it an ergodic theorem? Because you have time averages equal to space averages. Whenever you have that, you're doing ergodic theory. And since you're uniquely ergodic, this will hold for all points and all continuous functions. And another way of thinking about this result is you can say that for every point, the orbit of this point under omega of n is uniformly distributed in the space. Okay, so theorem A, it's aesthetical and it applies to every uniquely ergodic system. But maybe to give you a little bit more of an idea what it can actually do, let's just apply it to the simplest system, simplest non-trivial system that you can imagine. To me, the simplest system I can imagine is rotation on 2 points, where the space just consists on 2 points and the transformation just switches those 2 points. Well, it turns out if I apply theorem A to this almost trivial system, I get something very non-trivial, namely the prime number theorem. And let me convince you maybe very quickly why this is true. Well, the way I model rotation on 2 points, I take the space to be equal to 0 and 1, just those 2 points. And the transformation is just x goes to x plus 1 mod 2. And I want to point out that this system is indeed uniquely ergodic. And the unique invariant measure is just the obvious one that gives each one of the singletons the same mass, namely 1/2. And then to apply theorem A, I also need a point and a function. The function I'm going to use is just the function that takes 0 to 1 and 1 to 0, and the point is just 0. And then all it takes is a simple calculation to realize that this ergodic average here is actually equal to the number of n's for which omega of n is even. It just counts the same thing. And since the integral of the function I constructed is 1/2, theorem A tells us that this density is equal to 1/2, which, as we have seen in the previous slide, is equivalent to the prime number. Okay, now maybe you might wonder, can we also recover these other results I mentioned on my previous slide, the Belay-Selberg result and the Erdős-Lange result? Yeah, it's also, you don't have to consider very complicated dynamical system. Instead of just rotation on 2 points, you take rotation on m points, and you get the Belay-Selberg theorem. I included the proof here, so you can check it if you want. And also, if you want to recover the Erdős-Lange result, all you have to do is you have to apply it to so-called irrational rotations. That's another very commonly studied dynamical system in ergodic theory. And this dynamical system is just a rotation on the torus. It takes x plus alpha mod 1. That's what I mean by an irrational rotation. It's a simple dynamical system, but theorem A applied to it, almost immediately you get the Erdős-Lange theorem. Okay, any questions so far?
Yeah, if you have a classification of the invariant measures like you have in Ratner theory or something, which might not just be uniquely ergodic, a little more complicated, then do you have an analog of theorem A?
So as a matter of fact, if you're not uniquely ergodic, then this limit might not exist. Suppose you pass to a subsequence for which this limit exists. Then what I can prove is that you always converge to an integral of some invariant measure. So if you have a good understanding of what is all the class of invariant measures, then yeah, this could be useful.
So it's exactly of that nature that every limit must be classified if you happen to have a classification. Okay.
Yeah. So
and entropy is nowhere in sight yet, right?
No. So
your system could be a positive entropy.
There's no entropy. It could be positive entropy, zero entropy, whatever.
Okay.
So it's a very general dynamical phenomenon, I think. Okay.
I have a question. What are you using about omega n in order to prove such a result?
Am I using what? Sorry, I didn't hear you.
What information about omega n are you using to prove?
So I'm hoping to actually go over the entire proof of theorem A, modulo some technicalities at the end of my talk. So hopefully I can be impolite and ask you to wait a little bit, and hopefully you will see what I use about omega of n. It's very basic properties.
Just let me interrupt. I'm not interrupting. People think I interrupt. I'm just trying to interact. The words interact, not interrupt. Hello, Andrew. And after, when we finish here, the plan is we may continue for 15 minutes to talk. So don't rush if you can avoid rushing at the end.
Okay, thank you. That's always great to hear that I have an extra 15 minutes. Which speaker would say no to that? Okay. We also can recover, we get for free a couple of new results that were previously, as far as we know, unknown. There is one result to the Koenig and Kadai, which says that omega of n squared alpha is also uniformly distributed, but they were only able to prove it for certain alphas, irrational alphas, subject to certain Diophantine restrictions, namely that it's a non-Liouville number. However, if you apply theorem A to unipotent affine transformation on tori, so just another class of dynamical systems, then you get a polynomial generalization of the Erdős-Lange theorem almost immediately, and the statement is as follows. If you have an arbitrary polynomial, then Q along this polynomial, along omega of n is uniformly distributed if and only if one of the non-constant coefficients is irrational. And there's another new result we recover if you apply it to certain constant length substitutions. So another very well studied class of uniquely ergodic systems in ergodic theory. It's not important what kind of class this actually is, but then we can say something about the digit expansion of the values of omega of n. So I also included the statement of the result here. So it says that if SQ of n denotes the sum of digits of n in base q, then Q of n has no bias here as well. So this is a generalization of a classical result of Gelfand. And it says that SQ, evaluated of Q of n, distributes over all residue classes equally. There's only one more thing I want to say about Theorem A. It's a little bit foreshadowing for the proof of Theorem A. So our methods for the proof of Theorem A are new, and in particular, they don't black box any previously known results from analytic number theory. So our proof is elementary and self-contained. Okay, so Theorem A may be cute, but it's not really what we were interested in. It's only the beginning of a bigger dynamical phenomenon. And so I want to go on and talk a little bit about that. To remind you, this was the definition of an additive topological dynamical system. It just consists of a compact metric space and a transformation, which you can think of as an Sn plus action. Now, in contrast, I want to introduce a multiplicative system. So for me, a multiplicative topological dynamical system is very similar. It's a compact metric space. And then instead of an n plus action, you have an n times action. And what we were interested in, we wanted to understand how those different, the additive and the multiplicative actions, how they interact. Because there's this heuristic in number theory that the additive and multiplicative structures, they should be independent. Maybe we were trying to somehow observe that from a dynamical point of view. Well, let me give you an example. Maybe you want to ask, what's an example of a multiplicative system? As a matter of fact, we have already seen multiplicative systems in disguise in Theorem A, because observe this function capital omega of n. It has this property here, right? It's an additive function, which means it turns any n plus action into an n times action, right? Because if I have t to the omega, it turns this equation into this one here. And this gives a very natural class of, a very natural way of constructing examples of multiplicative systems. Namely, I take any additive system, I raise it to the omega, I get a multiplicative system. Moreover, I want to point out you actually get a very diverse class of systems, because a lot of properties of the system xt get carried over to xt omega. For instance, if you're minimal or equicontinuous or distal or topologically weakly mixing or whatever, all of them get carried over here. Any questions? So that's a first natural way of constructing multiplicative systems. There's another natural way. Take any completely multiplicative function, taking values in the unit circle. Also in multiplicative number theory, you know, it's all about the study of multiplicative functions. Well, for any such function, I can construct a multiplicative system. Very simple in just defining the action to be multiplication by the multiplicative function. So it's kind of, it's the analog. On the previous slide, I gave you the, I told you about rotation by alpha, an irrational rotation. You should think of this as being a multiplicative analog of that, essentially. Okay, so just some examples of multiplicative systems, so you get a little bit of an idea of what we deal with. Okay, and here's a reminder of the statement of Theorem A. And with this new observation that t to the omega is actually a multiplicative system, it raises the question, well, in Theorem A, can we replace this multiplicative system x to the omega with more general systems? And we have a result like that as well. but we need to impose some restrictions. We need to impose some restrictions because in general, it's not true that there is an analog. So we consider a very special class of multiplicative systems, and they're so-called finitely generated. It's just where the functions on the primes, there are only finitely many functions on the primes. I think of SSP as the generators of the multiplicative action, very naturally, because the primes generate the multiplicative structure in the integers. And if there's only finite many generators, that's what they call a finitely generated system. And so a generalization of Theorem A says the following: if I have a multiplicative system and it's finitely generated and strongly uniquely ergodic, which is just a slight strengthening of unique ergodicity. I don't want to go into too many details. I think that takes us away, but it's a natural notion of unique ergodicity for multiplicative systems. Then you have the exact same statement. So the Cesaro averages converge to the right interval. Time averages equal space averages. Just as a side note, I didn't include it in my slides, but for instance, as a corollary of Theorem B, we get Wissing's mean value theorem, and we also get special cases of the mean value theorem of Halash. So there are other classical number theoretic results we recover from Theorem B, and there's also some other curious applications, new applications we can get. Okay, so here's Theorem A and Theorem B. Any questions so far?
Sorry, you might have said this before, but what is that with condition? I can't understand what that means. The SP for P prime is finite?
Yes, maybe to better understand this condition of being finitely generated, we can look at it for this particular class of systems x to the d omega, right? X to the d omega is a multiplicative system. And I claim for any additive system whatsoever, xt to the omega is going to be a finitely generated multiplicative system. As a matter of fact, I claim it only has one generator, because look at xt to the omega was defined on the previous page, right? It's this action here. But what if I put a prime number in here? T to the omega of a prime number is just t to the 1. Right? So for this particular case, this set here is just equal to the singleton t. In other words, for every prime number, this multiplicative action does exactly the same.
Right, okay. Thank you.
And this is just a slight generalization, where instead of just one generator, you have finitely many. Yeah.
Excuse me, do you get from Theorem B, do you get the Dirichlet theorem, let's say counting primes which are congruent to one mod given number?
No. So what we get from Theorem B is something like the Wissing mean value theorem or the Halash mean value theorem, any kind of mean value theorems that study the averages of multiplicative function. The Dirichlet prime number theorem is about correlations of multiplicative functions with additive characters. So this is a slightly different game. So Theorem B does not imply the Dirichlet prime number theorem, but actually what I want to talk about next, this is going to go exactly in this direction, because the Dirichlet prime number theorem is something about the independence of the multiplicative structure and the additive structure.
Nice.
So,
thank you.
Short answer is Theorem B does not imply Dirichlet prime number theorem.
Thank you.
Thank you. Any other questions?
It's not quite true what you're saying.
Yes, please.
The Dirichlet theorem's equivalent to some things like chi times mu, where chi is a Dirichlet character.
Right.
So it would appear you're claiming to have some form of prime number theorem outside of progression.
So your objection is that Dirichlet characters are multiplicative as well.
No, my objection is that just like the prime number theorem can be re-expressed using mu of n or lambda,
Yes.
or -1 to the omega n in your language, you can re-express the prime number theorem in arithmetic progressions using the Dirichlet character times -1 to the omega n.
Yes,
No additive characters.
Yeah, thank you. Thank you for pointing this out. That's actually an important point. There are certain multiplicative functions that that we have to exclude, and I'll talk more about that later. They fall into this class that I use the umbrella term local obstructions. So Dirichlet characters are, to me, they are both multiplicative and additive. And
maybe we could, since you're going to mention something about an elementary proof along these lines of the prime number theorem, do you have an elementary proof of the Dirichlet along your?
I have not tried to write up the details, but I think the methods could work as well.
Okay,
Yes.
I think that would clarify everything. Yeah.
Yes. And I have to think about it. So if you construct a system like in this second example here, for the multiplicative function, you just take, say, the Liouville function times a Dirichlet character. This gives you a multiplicative system, and you apply Theorem B to it. Then maybe the Dirichlet prime number theorem follows. So I think I forgot who asked this question, but I think that's what they were trying to say. And I have not thought about that, so I will think about that. Thank you very much. Okay, to jump into my next topic, I want to remind what is the definition of the Liouville function. It's just the sequence -1 to the n raised to the power of omega of n. So -1 raised to the power of omega of n. And Sarnak's Liouville disjointness conjecture tries to capture the randomness in the omega of n function in the following way, using the language of dynamics, topological dynamics. And the statement of the conjecture is as follows: any zero entropy additive topological dynamical system xt and any sequence observed from such a system should be orthogonal or disjoint from the classical Liouville function. And here, zero entropy is just a measure of low complexity. I didn't include the definition because it's a little bit cumbersome, but it's just a natural class of systems that you should think of having a low complexity. Okay, I want to now point out that in light of theorems A and B, it's we have learned that sequences of the form like the Liouville function a natural generalization of such sequences are sequences of the form G, S, and Y, where S and Y is now, Sn is a multiplicative action. And so this raises the question, well, what if I have an additive system and I have a multiplicative dynamical system? Can we say something about the correlations of sequences observed in the additive system and sequences observed in the multiplicative system? The idea is, I want to say that additive and multiplicative system kind of behave independently. That doesn't mean that this limit always goes to 0, because the limit here will depend on the value of the functions f and g. So I want to introduce, instead of just having 0 here, I want to introduce a notion of independence. That's my next definition here. I want to call two arithmetic functions a and b asymptotically independent if the Chisauro average of the product is very close to the product of the Chisauro averages. And I just want to point out that the Liouville disjointness conjecture from the previous slide is equivalent of saying that the Liouville sequence is asymptotically independent to any sequence coming from a zero entropy topological dynamical system. It's just another way of saying it, because in this case, you will have exactly that this is equal to 0, because the product of the integrals will be equal to 0. And this leads me to the definition of what I imagine to be the disjointness between an additive system and a multiplicative system. That's a little bit of an odd notion because you're comparing two completely different actions. Nonetheless, if I have an additive system and a multiplicative system, I want to call them disjoint if any sequence coming from the additive system is asymptotically independent to any sequence coming from the multiplicative system. This I want to call disjointness. Okay, this is in line with Liouville's disjointness conjecture from the previous slide. Why? Well, remember, a couple slides back when we were talking about applications of Theorem A, I was trying to convince you that rotation on 2 points is the simplest additive system. Now let me try to convince you what's the simplest multiplicative system. It's again just on 2 points. So consider a multiplicative system where the underlying space just consists of 0 and 1, and for every prime, you are applying the exact same transformation. It's just rotation on those 2 points. This gives you the action, which is just Sn of x is x plus omega of n mod 2. And I want to call this a multiplicative rotation on 2 points, just to emphasize that this is the multiplicative analog of additive rotation on 2 points. And as it turns out, we can reformulate the Liouville disjointness conjecture of saying exactly that multiplicative rotation on 2 points is disjoint in the sense defined here from any zero entropy additive topological dynamical system. So that's, those two turn out to be immediately equivalent, because in this system on 2 points, I can generate the Liouville function. Like we have seen with applications of Theorem A. So this is very closely related. Okay, and what's the heuristic behind it? The way we see it is zero entropy is a measure of low complexity. So you have a low complexity additive system. And rotation on 2 points, multiplicative rotation on 2 points, that's in the multiplicative world, a very low complexity system. So the heuristic that I want to propose is that if you have a low complexity additive system and you have a low complexity multiplicative system and there are no local obstructions, so now this has to do with certain just almost trivial, especially with Dirichlet characters. So this, for instance, if the multiplicative system will come from Dirichlet characters, then this heuristic will not apply because I consider this to be falling under local obstructions. Then what we claim is those two systems are disjoint. Okay, I have to make a little bit more precise what low complexity means in both cases and what local obstructions means in both cases. Well, low complexity for additive systems, I just claim it's zero entropy. Low complexity for multiplicative systems, it's what we have seen in Theorem B. So in Theorem B, we have, let me go back. In Theorem B, we have considered finitely generated multiplicative system. It turns out that any finitely generated multiplicative system is actually of very low complexity. So we want to restrict our attention to such systems only. So now I still have to convince you what it means to avoid local obstructions. So here's a definition. I want to call an additive system aperiodic if any sequence coming from the system is asymptotically independent from periodic sequences. And then I want to do the same for multiplicative systems. I want to say they are aperiodic if the exact same thing holds. And then the conjecture that we propose, it's an extension of the Liouville disjointness conjecture. It says that if the additive system has zero entropy and the multiplicative system is finitely generated, and at least one of the two, it doesn't have to be both, but one of the two is aperiodic, then xt and ys are disjoint. Okay, and to substantiate this conjecture, we prove two special cases of it. We say that conjecture 1 holds for all Néel systems, so where xt is a Néel system. And it also holds for all horocycle flows, algebraic horocycle flows on SL2R mod gamma. Okay, so it has gotten increasingly more and more dynamic, and
I'll ask a question here.
yes,
you
please.
might expect that other characteristic factors to appear, not just aperiodicity. Were they captured in this picture?
So I think if you restrict only to finitely generated systems, then aperiodicity should be enough.
I see.
If you want to consider systems which are not necessarily finitely generated, then I think you have to consider more improved, more refined notions of aperiodicity. We have some speculations like that. We included some speculations like that in our paper. It essentially has to do with, so if you want to look at the conjecture, Liouville disjointness conjecture, you want to ask, well, how can I generalize this conjecture to other multiplicative functions? If you stipulate the condition that the multiplicative function only takes finitely many values, then aperiodicity is I think it's conjecture that this is a sufficient condition for this to be true. And something very similar we are doing here, we restrict to finitely generated system, because in this case, the notion to avoid local obstructions is just much simpler and friendlier.
Sorry, you seem to be saying two different things. Finitely generated for the multiplicative function means that finitely many different values for f of p if it's a multiplicative function, or finitely many different values for f of n?
So if you have a generalization of the multiplicative, here another multiplicative function, which I think only takes finitely many values on the primes, then again, multiplicative, aperiodicity should be sufficient to give an analog of this.
You can get functions that pretend to be a character,
right?
And those will give non-zero average.
Right.
So it's a little more subtle for sure.
Yes.
So you get something that's almost a character, but on a bunch of primes isn't quite. But say finitely many primes isn't quite, you can still get a non-zero average. So there's more to consider. There is a conjecture to make, but it's more complicated for sure.
Thank you. I'll think about it. I was not aware of that. So just to clarify, you say even if the multiplicative function takes only finitely many values on the primes, it could fail to be orthogonal to all deterministic sequences?
Suppose I took the character mod 3 and I just changed it on 2. Instead of chi of 2 being -1, I said chi of 2 is 1. Then I'm pretty sure you get a non-zero average when you put it up against e to the n over 3.
But I think the multiplicative function you get in this way will not be aperiodic, right?
Okay, well, I'll change it on infinitely many, but a very sparse set of primes.
I think you will still get what is called a Bezikovich almost periodic function. So it will still be essentially, I have to think about it. I have to think about it.
Well, there's a criterion called pretentiousness, and it has to not have distance, and that can't have bounded distance from a character. Otherwise, you'll
Right.
certainly fail. But anyway, so I suspect that generalizes to other types of additive characters, multiplicative characters. Multiplicative systems. You're going to have to be very careful about similar analogies to that in the ergodic setting.
I will double check. I thought I checked exactly that, but I will definitely check again. Thank you for pointing this out. Okay, where was I? Yes. So maybe with the remaining 20 minutes, I would like to go over the proof of Theorem A, with the understanding that I will brush over some of the more technical aspects of it. But please feel free to interrupt me at as many stages as you would like. So let me remind you of the statement of Theorem A. It's very dynamical, so I want to present a result that's slightly stronger and implies Theorem A and doesn't use dynamics at all. So if so far you have been very upsetting with this talk because it was too dynamical, hopefully this will be a little bit of a consolation prize. So here's a technical result which implies Theorem A. And there's no dynamics, it's just for any bounded sequence, complex valued sequence. If you look at the Cesaro average and you shift outside the omega of n just by +1, it will be very close, up to a small error, to the average of A evaluated omega of n. And this holds for any sequence A whatsoever. Okay, so this is the main technical result that implies Theorem A. Let me just mention, if you apply Theorem 1 to just the sequence A of n equals -1 to the n, you get the prime number theorem. If you apply it to other roots of unity, you get again this Belay-Selberg result that I stated at the beginning. If you apply it to e to the 2 by I and alpha, you get the Erdős-de result. And finally, if you apply it to sequences of the form A of t and x, coming from a uniquely ergodic system, then exactly because you're observing this shift in variance, and the uniquely ergodic system only has one invariant measure, it has to converge to this integral here. So applying Theorem 1 to this particular sequence gives you Theorem A. So let me try to convince you why Theorem 1 is true. To start with, I want to introduce some convenient notation. For a sequence in the finite set, I want to abbreviate, I want to introduce an abbreviation for Cesaro averages and for logarithmic averages. For Cesaro averages, I'm gonna just write E sub NB. That's just the Cesaro average over a finite set E. And the logarithmic averages are defined very similarly. So it's just averages with logarithmic weights. And they show up quite naturally. So that's why it's convenient to have some extra notation for them. Finally, I also want to use this Erdős notation, which says that I want to abbreviate the first n integers with just brackets in. The starting point for the proof of Theorem 1 from the previous slide is a very basic observation. A very basic observation that says that if I have a large set of primes and I take an integer at random, so imagine you have S is very large and you take the first primes smaller equal to S, and you want to understand, well, out of this set of primes, how many of those primes divide this arbitrarily chosen integer? It turns out that the likelihood is very high that this is exactly going to be equal to the sum of the reciprocals of the primes that you consider. It's a probabilistic statement. It's not hard to prove. It has to do with the independence of the different primes. So this is the basic idea that I want to exploit. And I want to write it in a little bit more of a rigorous fashion using averages. So an equivalent way of saying that is that you have those functions. it's a balanced indicator function on the numbers which are divisible by a specific prime. So I think of this, I'm very ergodically minded. So the way I think of this as a function of the integers. And to me, the integers are essentially Hilbert space. And for two different primes, those are going to be two orthogonal functions. And if you have many orthogonal functions, they kind of make a basis. So you can approximate any function. That's kind of how I think about it. And so you have this logarithmic average over those functions. For almost every n, this is going to be close to 0. The reason why I say for almost every n is because there's this absolute value here. The absolute value guarantees that, well, the average over a positive expression can only be close to 0 if for almost every integer this expression is close to 0. So that's where the almost all n in n comes from. Okay, so this is often viewed as a corollary of the Duran-Kobilius inequality, but as a fact, it's much easier to prove than Duran-Kobilius. You don't need the full strength. Because Duran-Kobilius, because here n goes to infinity first, and then s goes to infinity. With Duran-Kobilius, they are of comparable size, so you're considering more large primes, which makes it much harder. This one here is easy. And particularly useful for me is an equivalent form of this equation, where you replace the absolute value just with a certain function, a of n. Why is this so useful to me? Because it says, well, if you want to understand the Cesaro average of a certain sequence, and you want to understand what it's doing, an equivalent problem is to understand dilates of these Cesaro averages over dilates for many primes. And it's particularly useful for sequences in this theorem 1, because here I have omega of n on the inside. And so dilates are really easy to handle. And so this form equation 3 doesn't suffice for our purposes. I want a slight generalization. So instead of just considering primes here, I want to consider dilates by other numbers too. So I want to consider a version of 3 where here you take the logarithmic average over more complicated sets B. And so this introduces the questions, for what sets B is this going to be small? Because it's not going to be true for all sets B. And this following proposition here actually gives us a criterion that helps us check for which sets B this is going to be true. It's easy to explain. So this difference between the average and the dilates of the average is bounded from above by this double average over a very curious function. It's the GCD of mn minus 1. And remember, we would like the left-hand side to be small. And that happens if the right-hand side is small. But when could the right-hand side here possibly be small? It could only be small if this function here is 0 very often. Because if it's non-zero, it's bigger than 1, which is far away from epsilon. In other words, what this criterion, the way you should look at this criterion, it means a set B is good for equation 4 in the previous slide here. If it has the following property, I choose two numbers, m and n, at random from the set B, and I will have a high likelihood of having picked two coprime numbers. That's kind of the heuristic behind it. Any set B with this property will essentially be good here. Okay, I've also included the proof. I maybe not go over the details here, but as you can see, it's just a couple of lines. You consider the square, you expand the square, apply Cauchy, first you apply Cauchy-Schwarz, then you expand the square, you switch the order of summation, and you get it. So the proof here, it's not very technical and not very long. The much more technical result is the following lemma, which is also needed in our proof of Theorem A, and it involves the notion of a 2 almost prime. A 2 almost prime is just a number that consists of 2 prime factors. And here's the technical lemma. For every epsilon, which is close to 0, and every rho, which you should think of as being very close to 1, I can find 2 finite sets, B1 and B2, with the following properties. B1 consists only of primes, and B2 consists only of 2 almost primes. Then here is the hard condition. On every rho-adic interval, B1 and B2 should have the same cardinality. It might be empty, so this might be 0. So for many rows, this might be 0, but wherever it's non-zero, suppose this one here is 3, then here it should also be 3. In other words, you just want to find a lot of, in the same rho-adic interval, we want to find a lot of primes and a lot of 2 almost primes. And the third condition is exactly what we need for the proposition on the previous slide. Namely that if I choose 2 integers from B1, I have a high chance of picking 2 that are coprime, and the same for B2. So B3 does a lot of the heavy lifting, but it's actually a very easy condition to satisfy. For instance, for primes, it's almost immediate. Think about it. For primes, the property of choosing 2 and having them coprime, unless you pick the same prime, you have it. And for 2 almost primes, it's also very unlikely. If you have a large chunk of 2 almost primes, it's very unlikely to pick 2 which are not coprime. So the tricky part is establishing 2. If you're happy to use the prime number theorem to prove this lemma, this is going to be very easy, right? Because then you know the exact asymptotic within any rho-adic interval, and you have it. If you want to use Selberg's fundamental formula, that's also not so hard because it gives you good estimates on the 2 almost primes. But both of them are overkill, because we just need some primes and some 2 almost primes which are close to each other. We don't need to know any kind of asymptotics. So it's much more of a softer question, and you can kind of do that combinatorially. Okay, and so now we have all the tools needed to prove theorem 1. From here on out, it should be not too long. Take an arbitrary sequence, and remember, our goal is to prove this difference here goes to 0. I'm applying the technical lemma. The technical lemma gives me 2 sets, B1 and B2, satisfying conditions 1, 2, and 3. Now I'm going to combine condition 3 from my lemma with the proposition from the previous slides, which tells me instead of Cesaro averages, it suffices to study dialates of Cesaro averages. But I'm going to do it in a tricky way. For this expression, I'm going to use B1, and for this expression, I'm going to use B2. That's the trick. So for the 1 plus 1, I use this one here, and for this, I use B2. Okay, and now, yes, please. Yes.
What if B1 and B2 are empty sets? Like what
I think
condition?
Yes, please.
Yeah, I just want to see what condition requires B1 and B2 to be large.
It's condition 3. Suppose B1 consists only of 1 number. Then this average here can never be small, because if I take 2 sets at random, 2 numbers at random from this set, they're not going to be coprime. So,
yeah, but what if they're empty sets? So then
it's non-empty here. So I have to stipulate non-emptiness. Sorry, that's cheap. I understand.
Thank you.
So yeah, it's kind of silly. If they're non-empty, then condition 3 forces them to be of some considerable size. Okay, and so I want to compare this right-hand side. I want to say this one here is very close to this one. How does that work? Well, B1 is only composed of primes. So this dialate here is equal to A omega of n plus 2. Whereas B2 is only comprised of 2 almost primes. So this expression is also equal to A of omega of n plus 2. So they end up being the same. This already gives us, so it turns equation 13 and 14 from the previous slide. So here were 13 and 14. No, that's not right. 11 and 12. It turns 11 and 12 into those two equations. Sorry, it was a typo. Into 13 and 14. And now they already look very similar because we have the same argument here.
Epsilon to the 1/2 come from?
The F.
Where did the epsilon to the 1/2 come from?
That is the error that occurs from applying the proposition. Let me go back. I should have mentioned that. Yeah. So from this proposition, I get whatever this is to the 1/2. And remember, this double average here was smaller than epsilon.
Yes, so it's still a small number. Very good.
Yeah, I kind of ignore all the errors here because they're not going to be effective anyways. So whatever error term we get on the prime number theorem, it's going to be very bad. So for me, they're just small quantities. And now I use the second property. So I want to show that those two are very similar, very close to one another. And now I want to point out that if P and Q are close to one another, since the argument of the average is the same, those averages are going to be the same. So in other words, if P and Q are in the same rho-adic interval, and rho is going to be very close to 1, then this average here is essentially the same as this average here. And this allows us to compare 13 and 14, and which gives us in the end that this difference here is, sorry, this should be a rho, not an eta. I don't know where the eta is coming from. Yeah, sorry, here as well. So this is O of rho minus 1 plus epsilon to the 1/2 plus something that goes to 0. And now all I have to observe is that I let epsilon go to 0, and it will give me equation 10. And that's it. So please let me know if you have any questions, but that's all I wanted to say for today. Thank you very much. Thank you.
Thank you very much. Are there any questions or comments?
I have an immediate one. So you sloughed over this, and it's something I want you to highlight a bit. So you have an elementary new proof of the prime number theorem where you said you could do that. If you assume the prime number theorem, you could do step 2 easily. But if you don't assume the prime number theorem, then it's much softer than what Selberg needed. But you didn't say what you used. So I looked a bit at your paper. You used Chebyshev actually. So maybe you can say something about that. Because in a way you found some path where you've kind of completed Chebyshev's argument coupled with his ergodic theory. Yeah.
So I was actually cheating here a little bit because this is the statement we have in our big paper, and it's not completely elementary, but I wrote up the elementary proof too. And in the elementary proof, you actually need to replace the 2 almost prime here with an k almost prime, where k is even. But it functions exactly in the same way. And the reason why I'm doing that in the short paper is because it's just easier to find k almost prime close to primes than it is to find 2 almost primes close to primes. And the way you can do that is if you Chebyshev gives you a lower estimate of the number of primes. So it tells you there's a good amount of primes. You just don't know exactly in which rho-adic intervals they fall. But then now we can start multiplying them with one another, and on a rho-adic scale, multiplying acts like addition. So if I look at all the sets, all the J's for which the rho-adic interval receives a good amount of primes, then the row-adic intervals, which receive a good amount of 2 almost primes, is going to be the sum set of the previous set, which is much larger than the original set. And then 3 almost primes is then the sum set of the sum set, and so on. So you kind of can, fixing rho, you get more and more primes, and eventually you will find that in every row-adic interval, you can have plenty of k almost primes. That's all there is to it. It's writing it down combinatorially is a little bit annoying, but that's the idea behind it.
And of course, it doesn't give a, you never kept track of the remainder term, obviously.
No, no hope there, I think.
But Peter, I have to confess, we are guilty of not being terribly interested in that. But because, and by the way, I don't.
Well, if you get a power saving, then you do something quite new. So I wouldn't poo-poo that error term.
I see. But maybe we had maybe wrong belief that
the Riemann hypothesis is way.
No, I think the more important thing is that after Selberg gave the proof, elementary proof, Erdős and Selberg, it quickly became a question of what, how does it compare to the usual proof, and it was shown essentially to be equivalent, giving the same remainder term. But this is really a much softer proof. I mean, there are other proofs. Maybe you've looked at all the proofs. It's closest to.
It's closest to Hildebrand, I would say.
Yeah.
But do you believe, Zeev, do you believe that really such soft things can create really serious, bounds on remainder terms?
I don't have to believe it. You have to believe it.
I see.
I'm hoping not, but
I see.
Someone proved me wrong, of course.
Well, I'd like to make a comment that this idea that you spread the weight by using some form of identity. Here you've used what you call Jurand-Kubilius. Essentially, this appears in Selberg, it appears in Delange, as you said, it appears in Hildebrand. So the packaging here is different, very different.
Right.
But the idea that you notice that integers can be written as p times another integer, and then you locate p in intervals that allows you to locate the other in intervals, that appears in a lot of the proofs.
I agree.
And philosophically, even, the reason why you need 2 prime factors is because if you look at Delange's proof, sorry, not Delange, Debussy. Debussy's the one who's clever with this.
Yes.
What you see is he's summing Mobius functions. So what he does is he takes the sum 1 prime factor and 2 prime factors, and if they're in the same interval, those Mobiuses cancel out. So you could rephrase, I suspect, your proof with the Mobius function, and instead of having to compare in the interval, the Mobius will just cancel it out for you. But philosophically, all of the elementary proofs do this thing of spreading the weight from x to the epsilon to x. So if you like using a logarithmic weight, averaging and comparing. And the tricky bit is comparing intervals with intervals. And you've done this by a slightly different idea of picking primes in different intervals. What most of the other proofs do is do it for a bigger stretch of primes by just using the facts that, like, the sum of log p over p, you can estimate. But
yes, yeah, I think that's a very accurate account what's going on here. But maybe something I've been interested in, and I'm obviously not an insider, is this heuristic that you just mentioned, this spreading out and looking at dilates. Can you somehow see it also in the analytic proof of the prime number theorem? I tried to look for it, but I couldn't really. So any insight I would greatly appreciate.
Yeah, it's an interesting question. I guess the best way to think of it is that zeta prime over zeta times zeta equals zeta prime. So you can think of looking at the coefficient. Zeta prime over zeta gives you logarithms of primes, right? And then zeta and zeta prime just gives you 1 with the weight. So when you multiply zeta prime over zeta times zeta, you're somehow spreading the weight of logarithms out, and then you're getting it to be something which is just log n. Sorry, you're spreading the weight of the logarithms of the primes. And, you know, inside the proof of the prime number theorem, zeta prime over zeta, I mean, this is sort of, you can make a parallel. And if you look at Ingham's math review, he does. And underneath it, that's probably where you're looking at spreading the weight. It's just the very simple convolution identity.
I have to look at that again. Yeah, thank you.
Selberg's elementary proof and the zeta proof you can translate directly with a positivity, with a square, with Selberg's identity. I mean, what is really nice here is you've realized that because it's such a soft proof, I mean, this is your only proof of your main theorem, right? So it works.
For Theorem A, yes. Mm-hmm.
Yeah. What I find, I think the right thing to do here is for Koji to end the lecture, and that anybody wants to chat afterwards, so that we should formally end the lecture, I think.
Sure. Okay, so let's thank Florian again for a wonderful talk.
Thank you very much. Thank you.